To the final presentation for today, Katrien Kolenberg on AstroSounds and sonification of variable star data.
Okay. Yes, so good evening. I am very aware that I'm the last talk separating you from going outside and having dinner. So I will try to make it as lively as possible and also as short as possible. But I want to talk about sounds of stars because we all study variable stars, and this variability is very often linked to vibrations, pulsations, which are sound waves. And so what I want to demonstrate in this talk is how we can turn these light data back into sound and what we can learn from this. And that's also a topic I'm very interested in, the sonification of data. So I would like to share it with this community because I think you might have interesting things to add maybe to this kind of research. And you might have heard this music before. It's called Stellar Music Number 1. It was a collaboration between Jean-Francois Koller, who is a composer, and Zoltan Kolat, my colleague, who is also studying RLR stars. And Zoltan, he provided data, light data of stars, and then Jean-Francois Koller made a composition with it. And all the different sounds with different timbres that you hear are actually different stars, different pulsating stars. It's okay. So when I speak about this topic to a very general audience, but you are not a very general audience, you are experts on this, then I start by saying that the universe is full of sound, but yet what we get from the sky is light. So we get light, which is electromagnetic radiation. We get light in the visible part of the spectrum. That's where we started as humans, but now we can also observe light in other parts of the spectrum. And that's most of the information that we get from the cosmos. Of course, nowadays we also have gravitational waves, which open yet another window on the cosmos. But most of what we know from the universe is based on this light. Another wave phenomenon is sound, but sound needs a medium, whereas electromagnetic waves, they can transport through what we see as vacuum. And just like we can only see part of the visible part of the spectrum, so we only see certain wavelengths, we also can hear only certain wavelengths. And our human ears are sensitive to vibrations to sounds with between 20 and 20,000 vibrations per second. When I speak, that is, I have a tuning fork in my in my bag, but I will not. I'll not go and get it, but if I use it, then it will vibrate 440 times a second, and it gives one pure A. So these are the sounds that we can hear very well. The older we get, the more that this upper threshold goes down. But this is what we humans in general can hear, and that is typical for humans. Other creatures will have other ranges in this sound spectrum. Which also means that when we are going to sonify stars, which vibrate very slowly, then we will have to take this into account, that we bring it into the audible range. Now, when we hear sounds on Earth, anything that makes a sound, like this glass, or like my voice, or like this kind of synthetic material, when you hit something, you will know the material just from the sound of it. And that's what we try to do with stars as well. So we try to go back from this characteristic sound, even though we're not used to hearing it, to the structure of the object that is vibrating in that way. And we do that already for planets. We are already doing that for Earth. So here you have the Earth, and the Earth also shakes occasionally, and from these earthquakes geoseismologists, geologists, they can derive the inner structure of our Earth. We can do that now also for other planets. For example, Mars, where we already have instruments. This is the InSight lander, and it already has recorded the first Mars quakes. And Mars quakes in a different way from Earth, which reveals the difference in composition and in structure. And this is, of course, for objects that we can touch, where we can go to, and where we can directly register the vibrations. Of course, when we talk about stars, it's another story because they're far away. And stars have very long lives. They might vibrate only in a small part of this life, so it's only in specific phases that they will start vibrating. And these sound waves are the same as the sound waves that we describe on Earth, so we can use the same mathematics, it's the same physics that is operational in space, but they're much, much slower, because depending on the type of star, as you very well know, one pulsation might take a few minutes, days, months, years, or even longer. And there's no medium in space, so there's no medium to transport these sound waves all the way to our planet. So what can we use? We use the light, of course. And so we can see these stars sing. As they contract, they get hotter and thus brighter generally. And as they contract, they get cooler and dimmer. And that's how we get to these light curves. So the luminosity is a function of the radius and the temperature. And the combination of these two make these variations happen. And that's something that we can record. You do that with the cameras attached to your telescopes, with the eye also sometimes. And from that, for more than a century, we've been able to reconstruct these light curves. But actually, they are a symptom of the sound waves that are resonating inside of the stars. For most of the vibrations that we see, they're actually linked to acoustic waves or sound waves. And when we look at these data, these light curves, they are all very different, even within one class. The light curve is a bit different often, so you can tell this star is this one and not another one. It's a bit like you can distinguish different musical instruments, but within the class of the violins, you have the Stradivarius and you have the other cheaper, maybe Chinese violin, or you have different, different sounds that are very, very subtle, but that really reveal the differences in details in the structure. And that is something that I'm also interested in. Could we hear it? Could we hear the difference? And what I'll make you hear are different classes, but you could also wonder, could we hear differences within one class? And hear differences, for example, between an RRC star with additional modes or without these additional modes. So yeah, every star has its own particular sound with its own timbre, its own sound color, just like each musical instrument or just like each human voice. And depending on the structure, stars might have a lower pitch or a higher pitch, and also their very specific timbre. And yeah, as we've seen through many talks today, this is due to pulsations. We do seismology to actually get to this structure. And that's what these sound waves are also linked to, because from these sound spectra, we try to do inverse modeling and get back to the star that is vibrating in these sounds. So we try to identify these modes, and we start usually from the light curve. Then we have a spectrum, and the spectrum can be different depending on the type of star. And what we now will do is we will take this sound spectrum, and it's actually a light spectrum. It's a spectrum of the light data, but we will take it as a sound spectrum because that's what it actually is, and we will turn it back into sound, but audible sound. And in order to do this, you need to take this spectrum and speed it up, because these sounds are very low-pitched. You need to speed them up, basically transpose them at least 20 octaves to a higher register, or speed them up at least 1 million times for many of them. And then you will be able to hear them. Then you can listen. And so what you do there is you change the pitch of the star, but you do not change the timbre of the star. The specific sound quality remains the same. It's like playing the same chord on a piano, just 20 octaves higher, and you still can hear that it's a piano. And that's why the exact factor of speeding up is not that important, but it's important to take all the frequencies and their ratios into account because they define what is the timbre or the structure of the star. And we've done this for a few stars. So this is a first example. This is a red giant. It's Hydrae, which was observed by Connie Aerts, who was my thesis supervisor. More than a decade ago, this star was observed, and yeah, you hear the sound. It's like a really low beat. It's a red giant, this star. We also have models. This is a hydrodynamical model of what the pulsations in such a red giant could maybe look like. That's one example. This is what our sun might turn into in 5 billion years. Then another example, is this. This is, again, a model, well, an artist's impression of white dwarf. And so for this particular star, the authors also sonified the data, and then they said, well, this kind of timbre, this kind of spectrum, you can only expect for a star that has crystalline carbon at its interior, so it is a diamond. It's a diamond star, this one. Then I'm, of course, crazy about RLR stars, and I already showed this animation before, but now we also hear the sounds of the RLR stars. And it's immediately clear that these different types with different light curves produce different sounds when we make them audible. So yeah, you have this whole cacophony of many, many different stars, and we can try to make them audible, and that's what we have started doing also with some famous stars like the sun. These are the many frequencies in our sun. You might know that our sun pulsates in millions of frequencies simultaneously, so this is just a subset that is sonified, but it already gives an idea of the timbre. And yeah, of course, when we justify this for a larger audience, the argument is always, yeah, stars are the building blocks of the cosmos, and if we want to understand even the future of our own sun, which we just heard, we have to understand how it fits into the whole story of stars at different ages, in different life stages, different types of stars. And the only way that we can get this from a dot of light is through studying their variations. And that's what we can also do by studying these sounds. And yeah, we looked at a few more stars, so we got data. Some of the data were obtained on Earth, other data were obtained by space missions. These were data from WIRE that we used, combined with some other bright data, I think. And so we looked at Polaris, which is a Cepheid. It's a triple star, but one component is a Cepheid, and this is what it sounds like. Then another famous star is Beta Cephei. It's also called Alphirc, which is also quite bright. So these are stars that the large public might even know, that they can see with the naked eye. And this star is not as evolved as the previous one, not as evolved as Polaris, but it's still on the main sequence, and it's a massive star, so it's very important for the production of heavier elements, and the sound is also very different from the one of Polaris. And then, of course, our favorites are Larry. Here you see it sped up because each one of these blinks takes 13.5 hours. This is a modulated star, as you saw before. We used the Kepler data to sonify them, and this is what we got. it's very clear that all these stars sound really different. And so you don't need to be an astronomer to be able to hear this difference. Which is why already years ago, when I used these sounds just to talk about my research to the larger audience, I started wondering maybe we could just, instead of looking at a screen and looking at graphs and looking at spectra, we could also sonify the data and see if we could use this sound to see better, to have a better way of discriminating between different types. And around that time, that was more than 10 years ago, I also met Wanda Diaz-Merced, who is blind, who's an astrophysicist, and she also did studies on sonification. And at the time, we were both working in Boston at Harvard, and she was doing experiments with trained astronomers to look at data of, I think it was black holes swallowing matter, so accretion on black holes. And you could see some kind of thing in the noise when this happens, but actually when we looked at the sonified data, and I did the experiments as well, I was very convinced that it helped me a lot to better discriminate the real signal from the noise. And that's why we started collaborating and also looking at different ways to make these techniques of sonification be more understood and be more studied. Because of course there are many ways of sonifying data, and which ones work and how powerful is this technique to be used really next to all the kind of analysis, usually visual, that we're doing already. And we tried to get funding for this kind of research, but it was not easy because, of course, this kind of research is very multidisciplinary. It's not just astrophysics, it's actually more perception, which we are not experts on. It's also about how do you sonify, it's technology also. There's much more to it, there's biology to it, than just stars, which makes that it's really hard to get funding for this kind of research, even though we tried through various channels. But then in Belgium, where I currently live, we got funding from the government to make it into a citizen science project. So to sonify data of stars and then see if the large audience would be able to hear these stars. And of course, this has a big opportunity also for doing outreach and to make people think about stars and also participate in the research. So that's how we started this project called AstroSounds. It is about listening to the stars, and it really targets everyone. And we started at the back end by looking at data of stars and looking at ways to sonify these data, experimenting with that for more than a year, to then come up with modules that everyone could do. And in parallel, we developed educational modules for children of different ages, both primary school and also secondary school. Because this is such an interdisciplinary kind of research, it is a typical STEM project for schools, because you have physics of stars, but you also have mathematics of how will you analyze the data. At the same time, you could teach the kids how to program, because if you want to make your own star, then you might want to generate frequencies. So it's a real STEM or STEAM project. STEM is science, technology, engineering, mathematics. It's a buzzword in many educational systems. And then STEAM is the same with the A of arts added to it. And so that's a creative approach to STEM. And in education, it is very much desired that even though kids at school get maybe only mathematics, and then in a separate class they get physics, and in a separate class they get biology, it's very useful to show that all these disciplines actually are linked to each other. And so this is a project that allows to do that. And that's why we could really enter also into schools and have them do the experiments. So we made modules in which pupils have to learn how to listen, and it starts with musical instruments or voices of men versus women, And then you can see how well you are, how well your ear works. We start with things that are familiar, but then we very quickly inject the teasers that are the stars. And then it's very clear that it's equally easy to distinguish one star from another as it is to distinguish one voice from another. And so we have these training modules and also experiments online that people can do. They can register, make an account on the website, which meanwhile has been translated to English as well, and they can participate. And we have spread this through various channels. It's been picked up by the media too sometimes. So in that way, we have already several hundred people who have done it, but of course we would like to do more. So we have the way we've rolled it out in Belgium is by having these modules to have kids make their own stellar music. We train educators on this also during COVID. And then we have also some things that we can put in the public. This is a booth that we developed in collaboration with students in the art school. So it's really a STEAM project in which people can listen to two different stars. One is a solar-like star, the other one is an Aralare star. And then they can participate in an experiment in which they will classify these stars. And these, this one is now currently at the planetarium in Brussels, but before it's been put in public spaces like the library, where people who are not into stars or not even remotely interested, where they might be triggered and to go and listen. And so we've also done experiments on how well does this work when you bring the science into the public space. So the website is open to everyone. But while doing this research, actually we saw that it is much more than just stars, sounds, perception, maybe biology of the ear. It is even how people communicate about sound. What kind of vocabulary do they use when they describe certain sounds? How can you say that this sounds different from this one? You can hear it, but often you need the words for it as well. So this is yet another part that we are now doing in collaboration with people who study these semantics. And this is a link to a survey trying to probe how people experience certain sounds. And it's also very culturally determined. So it turns out that this kind of research is much more complicated than we even thought at the beginning. But it is worthwhile, because of course when you sonify data, you open the field of astrophysics to people who have visual impairments. And you can make science much more inclusive. And when I witness how Wanda can pick up subtle sound differences, it's clear that people who might not have their eyes at the same strength, they will have a much better trained ear to be able to distinguish things. And using different sensory channels to analyze data is definitely worthwhile to get better results and also to make science more inclusive. So that's also where this AstroSound project fits. That's all I wanted to say. I think if you have, you're very welcome to go to the website and try it out, give feedback. I know the website is open for improvement. Also for some stars, because we have this project of really turning very famous stars into sounds. And for these, usually the space missions don't have the data, because these are the brighter stars. So that's where we will also go to the older data, the AVSO, the GEOS, and see if we can get data there to be able to make a spectrum and then to sonify it. So thank you.
Thank you very much for the presentation and the music. Do we have any questions? Yeah, there's someone in the back.
Thank you very much. The difficulties you are experimenting to find sounds for this
Yeah.
project is what made Kepler's so difficult to understand by the following astronomers. I have a scientific show I made with an alter ego friend. We are a historian of astronomy, physics teacher, and jazz musicians, and we have a scientific show called the Kepler Music Project, in which we apply the Kepler, the method that Kepler developed in the Harmonices Mundi, the harmony of the world of 1618, to exoplanet systems. We make exoplanet systems sing as Kepler makes sound with the solar system. You do the same thing. It's the same method. We Kepler need to transpose the motions of the planets. It takes Saturn to be the lower sound, but Mercury, the motion of Mercury is so fast that its sound in Kepler's method is too high. So you need to transpose the sound you want to. You think. Johannes Kepler is the extreme way to apply the Pythagorean project of music of the spheres.
Yeah. Yes.
And you do the same thing. It's the same spirit. It's the same epistemology. And I think you could find historical arguments to develop on an epistemologic way your project, to show that this exploration, this scientific exploration, it's of the same kind of the Kepler's method, which leads to the third law, which is a universal jauge. But the scientific method is a foolish one, because he makes an analogy between astronomy and music. And it's the reason why we know Isaac Newton doesn't read Kepler and doesn't understand Kepler. And, well, some vrac arguments comme ça. Voilà.
Yeah, thank you for that remark. I would like to see your presentation or your show. That sounds really...
So
like
wow effect.
Sorry?
The show is a wow effect.
Okay, yeah.
It's an electro jazz by the electro jazz concert.
Yeah. Yes. I see. Actually, I think this was not the last slide, but it is actually an animation. So I'll try, and I think it will come up, yes. Because you can sonify stars, but as you might know, gravitational waves also shake up space-time at the pace of an audible sound. And so that's another thing, and that's what Wanda has been working on. She's been working on the sonification of gravitational waves. So in that way, it fits into citizen science, which is already, as we saw also this afternoon in various talks, in astronomy is very, very present. And so this is why also we do it for the sounds of the stars as a citizen science project.
I want to congratulate in this project that you've been working on. What I can see is that really this is like a revolution for the education for the kids. Because like you say, everything is separate, you know, like math And I think that, wow, this is amazing. I am just, wow, I don't have words for describe.
Thank you.
But I think that should be more like English or the language, maybe Spanish or something going, you know, around the world, because
Yeah.
this is amazing. I had a couple of friends that they are into stars, and I'm very happy to share this information to
Yeah.
them because it's, wow, it's incredible. So well done. Thank you.
Yeah, thank you. Yeah, we want to actually roll it out. It started also as an international collaboration. So we did get funding in Flanders, so that's why we started to roll it out in Dutch. And of course, every country has their own school system, and even in Belgium you have 3 languages, so it's different. But in general, this is something that you can transpose to other countries. So there are already plans to try and also implement it in India, for example, and in other places. And it would be really nice to do that. Yeah. So thank you. Yeah.
Any last questions?